Hello, this is Jared Plaisance and I'll be discussing material fracturing. This was a topic discussed in Chapter 8 of the MEMT 201 series. We will define fracturing as the separation of a body in two pieces due to stress while the temperatures are below the melting point. This occurs when material stress exceeds the yield strength. There are two common types of fracture: ductile, moderately ductile, and brittle. The ductile fracture has a slow crack propagation that happens alongside of a large placid deformation and usually fails after showing warning. This results in a cup and pin shaping of the material as we see in the left image. Moderately ductile fracture is like ductile fracture but has some brittle properties. Brittle fracture has a fast crack propagation and little plastic deformation. The fracture type fails before warning, as we see in picture right. This usually ends up in a shatter almost. When ductile materials fracture, it goes through a series of common steps. It begins by the material necking in its weakest points, then small holes that were previously already in the material come together and create a big cavity inside. Then, as it's stretched more, the material begins to give out, and that's when we get our pin and cup look in the fracture. And here's a video showing exactly what I'm talking about. Brittle fractures follow one of two grain surfaces depending on the force and stress. The first one, intergranular, follows the boundaries of the outside of the grains. The second one, transgranular, granular, does not follow any type of grain structure but instead split right through. This is usually caused from a higher stress. Fatigue failure is another type of fracture that is caused from a long period of high stress and strain. Common application of a fatigue failure is heavy machinery that is not kept up with. And here are a few images inside of what a fatigue failure looks like on the granular side. A way to measure the energy during fracture of a material is the Sharpie impact test. This test is completed by subtracting the final arm height by the initial arm height, and the readings are displayed on the swinging arm on the dial. That is a swinging arm. And here's a video of the Sharpie impact test. And as we saw, the dial is above the arm. That's what it's displayed on. Now, what are some ways to prevent this? We can reduce stress on the object altogether, of course. Heat treating to change the microstructure, and changing design so there are less sharp corners on the object, which will increase strength. That is all for my video. Thank you for watching. Have a good day.